Are we recording? We should be recording now. Yes, we are. Okay, so again, we are looking at the sheet that I attached in the chat, the group chat, but we're going out of order. So we're starting with number 3. Now, we're going to start with working what's known as piecewise continuous functions. Now, they are called piecewise continuous because while we can break up the function into different pieces, each of those pieces is continuous. And remember what we said about continuous functions. We can draw those pieces without lifting our pencil. So while the graph as a whole may not be continuous because it's defined in pieces according to different domains, the pieces of the function are in fact continuous. So I know that that naming convention can be a little bit confusing, but that's the true definition of these functions. So here you have been given the function h of x. Now this h of x, this function is defined by 2 pieces. There's the first piece, here is the second piece. Now, we're really not going to talk about graphing this one because we haven't really talked a lot about graphing. So Nathan, you don't have to freak out just yet. We're just evaluating the function for different inputs of x. But I want to get you familiar with what piecewise functions, piecewise continuous functions look like. They're the function notation, in this case, h of x, it's going to set equal to open parentheses, and in this case, 2 pieces. So if I were looking at the graph of this, I would see that it's defined by 2 different pieces. I'm going to look at the first interval for where it's defined, and it's defined for all values less than or equal to 2. So part of the graph, represented by 2x plus 2, is going to be in that region. The second part of the graph is going to be for all values of x that are greater than 2. So what is that's telling me is that's telling me that over here, the graph is going to look like one kind of graph, this 2x plus 1, and over here, the graph is going to look a little bit different. So do you see how I'm breaking the Cartesian plane into, in this case, 2 regions, the green region and the blue region, depending on how the x values are defined. Now, I know we're going kind of fast through these piecewise continuous functions, so at any point, if this isn't making sense, let me know. Let me know, okay? So does that make sense? So in this case, I'm defining the piecewise continuous function over 2 different regions. Now, you are being asked to evaluate this piecewise function for these 2 values of x. So for x equal to -1, which piece am I going to use? Am I going to use the first rule, or am I going to use the second rule? Am I going to use the equation that is highlighted in green, or am I going to use the equation highlighted in blue? Because I'm saying I want to evaluate when x is equal to -1. So which one am I going to use, the green one or the blue one? The top equation or the bottom equation? Can anybody tell me?
The green one.
The green one. Excellent. Very good. Because when x equals -1, that falls into this region. So to evaluate, so for x equal -1, I'm going to use h of x equals 2x plus 1. And I'm going to evaluate x for when x is equal to -1. So I'm just substituting in -1 for x. So when h is evaluated at -1, what is the output? Do we know? Can we evaluate that?
-1.
Excellent, -1. So if I'm evaluating the piecewise function for x equal -1, I do know that the point -1, -1 exists. So that is a point on the graph. Now, what type of equation is this?
Linear equation.
It's a linear equation, so I know the graph is going to be a line. Now, I know the graph passes through this point because I just substituted in x equal -1 into the equation. Now, can I graph the rest of that piece?
Yes, you just need to use x equals 4.
I'm going to use, well, x equal 4 is, I only want to graph the part in green. So if I'm graphing the part in green, I'm using this equation. So I'm graphing this line. So how am I going to graph that line where it exists in the green region? I have a point on the line, but I actually have the equation as well. So how could I graph that?
Start at the y-intercept of 1 and then go up 2 and over 1.
Beautiful. So I could do that. I could start at the y-intercept, so at 0, 1, and then I could use the slope and go up 2 and over 1. And then I could go up 2 and over 1 again. And remember, it's defined up into this x equal 2, right? So isn't this true? Isn't that piece right there? I could have also started at this point that I know exists on the line and gone up 2 and over 1 as well, right? So Reese, what you said was correct, but you could have also started at this point and just applied the slope. Do you see how I did that to get this part of the graph? I've now graphed the first piece of that function. Does that make sense? If not, speak up. Ariana, does that make sense?
Yes.
Yes. Natalie, does that make sense?
Yes, ma'am.
Okay. Nathan, we're graphing a little bit here. Does that make sense? Okay. Now, actually, I just asked you to evaluate it, so we technically didn't need to graph, but I kind of wanted to let you see that we are graphing, when we graph a piecewise function, we can have different parts of the graph depending on where we are. So now for x values greater than 2, so that means when x is equal to 4, I would use the second equation. So I would use h of x equals x squared minus 4 to evaluate when x is equal to 4, because when x is equal to 4, I'm in the blue section. Now, what type of equation is that? Looking at the equation, how would you describe that type of function? What's the highest exponent of x?
It's a quadratic.
It is a quadratic function. Since the highest exponent of x is 2, it's quadratic. So what is this graph going to look like? What do graphs of quadratic functions look like?
A parabola?
It is a parabola. So while the first part, the green part, was linear, the second part is quadratic. So in the blue region, we're going to see part of the graph of the parabola. y equal x squared minus 4. Now, I'm being asked to evaluate the function when x is equal to 4. Oops, that's a minus sign. So that's going to give me 16 minus 4, so that is 12. So when the function is evaluated at x equal 4, the output is 12. So I know that point falls on that part of the graph. So I can go over here and go to 4, and when x is 4, I'm way up here. I'm way up here at 12. I'm not even going to pretend to graph that accurately. But this is a parabola. So can I look at when x is equal to 2 so I know what's happening here, because it exists for x equal 2. So just for kicks, if I substitute in 2, because it exists there, it's an open circle, but it exists. I can say 2 squared minus 4, so I can say 4 minus 4. So when x is 2, I'm here. Oh. So this is a parabola, so it's going to look like that. Kind of curve. That's not a line, that's a curve. Now, am I really focusing on the graphing aspect of this right now? No. We're really making sure that you understand what a piecewise continuous function is and how to evaluate and pick which equation to use depending on the input that you're being asked. But do you see how it's two totally separate pieces of the graph? Any questions on that? Piecewise functions are super exciting. Okay. Ignore my phone that is ringing. Okay, so now let's go ahead and look at number 4. Number 4, you have been given, again, another piecewise function, a piecewise continuous function. It is defined by 2 pieces. So if I look at the first piece, can you tell me what type of function that is? How would we classify that?
Quadratic.
It is quadratic. Very good. And the second piece is what type of function?
Linear.
It is linear. Yes, it is linear. And again, I'm able to tell by looking at the highest exponent of x. The highest exponent of x in the first equation is 2, so it's quadratic. Its graph is going to be a little parabola. And the second piece is going to be linear because the highest exponent is 1. Now, where do I see the separation of the two? I see the separation of the two when x is equal to 0, right? So if I'm looking at the graph, if I were to be interested in graphing this, I would look at the graph and I would say when x is equal to 0, everything less than 0, oops, let me do that in green. Everything less than 0, so over here, is going to be linear. Everything to the right of 0 and including 0, to the left is going to be quadratic, to the right is going to be linear. So our 2 pieces of the function, they change, the graph changes when x is equal to 0. Do you see that? Because this is where I'm defining my domain. So that first function, the first function, g of x equal 3x squared, only exists to the left of the y-axis. The second function, g of x equals 5x minus 2, only exists on the y-axis and to the right. So do you understand how the left part is the equation, and then the right part here is defining the domain, the interval for where that function exists? Does that make sense? Okay, so if I'm being asked to evaluate it at x equal -1 and x equal 3, I have to figure out which of those two equations I'm going to use to find the output for when x is equal to these two values. So when I'm looking at the first one, when x is equal to -1, am I using the first equation or the second equation?
The first.
I am using the first one. So when x is equal to -1, I'm to the left of the y-axis. So I'm going to use the first equation to evaluate the function for when x is equal to -1. First of all, does everybody see how to choose the correct function to use, the correct equation? Then good, Eric. Then the second step would be to substitute into that equation. So if I substitute in -1 for x into the first equation, what is the output? You tell me. What would the output be?
Is it 4?
It is 4. It is 4. Excellent. Because -1 squared is 1. -1 times -1 is a +1. +1 times 3 is 3. 3 plus 1 is 4. So I know when x is equal to -1, I'm at y equal 4. So when x equals -1, I'm at 4. I know that point exists. Now, what about when x is equal to 3? Which equation am I going to use for x equals 3? The first one or the second one? To evaluate x.
The first one, right?
Well, the first one says it's only true for x that is less than 0. I'm looking for when x is equal to 3. So if x is equal to 3, does it satisfy x is less than 0 or x is greater than or equal to 0? That's the question you're asking. So when x is equal to 3, 3 is greater than 0. So I'm going to use the second equation. Does that make sense? Yeah?
Yes, ma'am.
Okay, good. So I'm going to evaluate my function at x equals 3 using the second equation. And when x is equal to 3, what is y? Oops, I didn't substitute in. Let me substitute. So when x is 3, what is y?
13.
13.
It is 13. So when x is 3, y is way up here at 13. Now remember, the graph in the green section stops at the y-axis. The graph on the blue region starts on the y-axis. So if I wanted to try to graph this a little bit, more accurately, let's start with the linear one. How would I graph that? How would I graph the blue part? Two different ways I could do it. How do I graph y equals 5x minus 2? I know this point, so I could use that point, or how did we say we could graph it? This is y equals mx plus b, right? So if I know b, what do I know? What point do I have? What does the b value represent?
The y-intercept.
The y value of the y-intercept. So I know that what point exists from that?
0, -2.
0, -2. The y-intercept is 0, -2. Now, since it's defined for x equal to 0, I can actually plot that point. That point exists. And then I could, what's the slope?
5.
5, or 5/1 if we want to see rise over run. So from this point, I could go 1, 2, 3, 4, 5/1. 1, 2, 3, 4, 5/1. 1, 2, 3, 4, 5/1. And I can see that part of the graph, right? It starts at the y-intercept and it goes on forever that way. Now the left part is this parabola. So if I wanted to get a better idea of the parabola, I could substitute in 0 in here, and I could get the y-intercept, right? Because the y-intercept is when x is equal to 0. So if I were to substitute in 0 for x into the first quadratic part of the equation of this piecewise continuous function, what would the y-intercept of that be? Anybody? If I substitute in 0 here, right? Because that would give me the y-intercept. What's the y-intercept of the green quadratic function?
0, 1.
0, 1. So I could go to 0, 1. Oh, but it doesn't exist there, right? Because that's only true for x is less than 0. So I'm going to have to put an open circle there, right? I can't have 2 points on the same x value or it's not a function. So I know the graph is going to look like this, right? Because it's a parabola and it looks like that. Do you see how I got that graph? We're doing little sketches, so they're not perfect, but Nathan, does that make sense how we're graphing this?
Yes, ma'am.
Okay. See, graphs aren't so bad, Nathan. They're fun. Shall we try the next one? If there are no questions, let's move on to the next one. I want you to try the next one. You try the next one. You are being asked to evaluate g of x at x equal -1 and x equal 4. So determine which equation you are substituting into, and I want you to evaluate g, we're not graphing, we're just evaluating because this is a different type of function. So I just want you to substitute into the correct equation and tell me what the outputs are. You tell me. So you're looking at the two equations and you're trying to decide which one you're going to use to evaluate g of -1 and g of 4, and then evaluate it. Do we think we have it? Okay, so for x equal -1, are we using the first equation or the second equation?
The first.
Yes, we are, because when x is equal to -1, you see the or equal sign? That or equal sign says I need to, that's included. So when x is equal to -1, I'm using the first equation. For kicks, does anybody know, can anybody tell me what type of equation is that? Y equal 2 to the x. Do you recognize, can you tell me what type of equation that is?
Is it exponential?
It is an exponential function. When the exponent is the unknown, it is an exponential function. So that means we're looking at either growth or decay. Very good, Eric. Okay, so let's go ahead and evaluate that. Now, how do I address that -1 as an exponent? Can I rewrite that without a negative exponent? What would that be? What's 2 to the -1 if I want to rewrite that without a negative exponent? Do we remember how to address negative exponents? Natalie, do you know how to address negative exponents?
No, I don't remember. Sorry.
That's okay. That's okay. Abiela, do you remember how to address negative exponents? No. Ariana, do you remember how to address negative exponents? Reese, do you know how to address negative exponents?
Doesn't it become like the numerator? And that's like 1/2.
So half of what you said is correct. Half of what you said is correct. So the fact that you're thinking fractions, that is correct. So when you see a negative exponent, to get rid of the negative exponent, you take the base. So this 2 has a -1. You take the base and you move that base 2 across the dividing line. Since the 2 is in the numerator, to get rid of the negative exponent, you take it to the denominator and then you make the exponent positive. So G evaluated at -1 is 1/2. So this point exists. I want to just take a moment to talk about negative exponents to make sure that we're all on the same page. Okay, so if I were to give you x to the -3 power, based on what I just said, if I wanted to rewrite that without a negative exponent, how would I write this?
One over x squared.
Exactly. So I'm taking the base, I'm moving it across the dividing line, and then I'm making the exponent, once I cross that dividing line, the exponent becomes positive. Does that ring a bell for the rest of you? Have you seen that before? Yes, have you seen it? Natalie, have you seen that before? Abiella, you've seen that before? Nathan, you've seen that before? Okay, well then, if that's the case, tell me, how would I address this? How would I rewrite that without a negative exponent?
Would it be b to the power of 2 over a?
Well, it would be b to the power of 2 because this has the negative exponent, so it's crossing the dividing line, and this moves up, and this becomes positive. But let me ask you, what is the exponent in the original problem? What is the exponent of a? If I don't see an exponent, what is it?
1.
So, is it positive or negative?
Positive.
So does it move?
No.
It doesn't move. Only negative exponents lose the minus sign, move and lose the minus sign when you cross the dividing line. I gave you that on purpose. It was a little trick. Does that make sense? You only move what has the negative exponent. So again, let me just give you something else. If I give you a z, what is the exponent? If I don't, 1. What is the denominator if I don't see it?
1.
What is the coefficient if I don't see it? Okay, so those things, they're there even though we don't necessarily see them. Okay, let's try another one. What if I give you, let's be real sneaky. Can we simplify that? In other words, rewrite it without the negative exponents. This is a tiny little impromptu lesson on negative exponents. How would I simplify that? We want to write this without negative exponents. This is huge. You need to know your exponents and your rules of exponents. This is super important. So this is a good refresher.
So I'm kind of guessing, but would it be 2 times b to the power of negative, or just 2?
Okay.
Over 3 to the power of x1.
Yeah, and that wasn't a guess, Eric. Why do you say you're guessing? You're applying.
Oh.
That's not
An
a guess.
educated guess. How about that?
You're saying that's what it is, and it's either right or wrong. Don't guess. You got it. So the exponent of 2 is 1. So it's not moving. It's staying there. Whether you see the 1 or not, it's not moving. However, this has a negative 1. So I'm going to move the x, and then when I cross the dividing line, I lose the little negative exponent. Same thing holds true with the 3. It has an exponent of 1, so it doesn't move. However, that b to the negative 2 in the denominator, again, it has a negative exponent, so when we cross the dividing line, we lose the minus sign. So that is correct. That is correct. Do we want to try one that's a little bit more interesting? Why not? Let's try another one. Let's try. Let me make this one a little bit more interesting. Actually, yeah, let's not, I won't make it any more exciting than that. Let's start with that one. Our goal is to simplify this and represent it without negative exponents. Let the fun begin. Christopher, I see that you're here. I don't know when you joined, and I know you're in another class. So just FYI, we started working on this piecewise function practice, and this prompted me to discuss negative exponents. So we kind of stopped on number 5, and we're doing some practice problems to review our rules of exponents. This one's exciting. There's lots of stuff going on in this one. Does anybody think they got it?
Maybe.
Maybe? Okay. Can you tell me what you did first?
I put all, like I switched all the places to the right in numerator and denominator, so if they have like a negative, I just.
Okay, excellent. So then you noticed everything that had a negative exponent and you moved it. Okay, yes. So what does that now give you? If you did that, what would be the next step?
And then
what you have at this point if you've moved everything.
I got 4 y to the second x to the third over 2 to the second y to the fourth x to the third.
Okay. Does everybody see how Reese got that? That is correct, Reese. That's what I would do. Do you have to do that first? No. Sometimes there's different ways to do them. Does anybody not understand what just happened? So everything that had a negative exponent moved. Since this was in the numerator, it came down to the denominator and lost the minus sign. Since this was in the numerator, it came down to the denominator and lost the minus sign. This one stayed here. This one stayed here. But then this one with the minus sign moved up here and lost the negative exponent. And last but not least, this one with the negative exponent moved up here. So can everybody get to this first step? Yes, that makes sense? Okay, now what would be the next step? So let me just rewrite that because I got a lot of colors going on and I don't know if that's confusing you. So I have 4y squared x cubed, 2 squared y to the fourth x cubed. Can somebody else tell me what we would do next? Does anybody have any ideas?
You could probably get rid of the x to the power 3.
Okay, how? You are correct. How? What do you mean get rid of it?
Well, technically, you could kind of separate the equation like by having let's say just 4 divided by 2 to the second power.
Oh, okay, so you're looking at this as just product of terms.
Mm-hmm.
So you're telling me if I understand you correctly, I can look at this as one piece, my constants. I can look at this as another piece because it has a base of y, and I can look at this as another piece because it has a base of x. Is that what you're saying? You're looking at it that way?
Yes, ma'am.
Okay, so you're going to simplify your like bases, so to speak, and your constants. And then one thing, Eric, I'm going to be very picky. This is called an expression.
Okay, sorry about that.
Not an equation, because it doesn't have an equal sign. So we're not solving anything. I'm just going to be picky because Reese knows I'm super picky. I'm super picky with language. So yes, this is actually a beautiful way to look at the next step. Okay, so does everybody understand what Eric's saying? He's saying, I can now simplify like bases or constants and then like variables. Okay, so Eric, how did you do that? So if I'm looking at, let's say, the 4 over the 2 squared, what does that simplify to?
It could simplify to 4 over 4, which is just 1.
Exactly. So this 2 squared, you evaluated the 2 squared, and I'm just going to show one more step. Okay, so you're saying you evaluated the 2 squared, and then they simplify, and that just gives you 1. Very good. Okay, so what about these terms? How does that simplify? We have y squared over y to the 4th.
You can break that down to y over y to the 2nd power, if I remember correctly.
Okay, so I'm going to do a little aside. And I'm going to take this because you're partially correct. So let me take this and go over here. Okay, so I'm going to be looking at y squared over y to the 4th. For those of you who don't remember your rules of exponents, you can always expand the multiplication to remind yourself of the rules. So y squared means I have y times y, right? The exponent tells me how many times I'm repeating the base by multiplication. So what would be in the denominator?
4 y's.
4 of them being multiplied, right? Okay, so that means I can simplify, right? I can simplify again, right? Y goes into y once, y goes into y once. So what does that leave me in the numerator?
Just y squared.
Well, these simplified, right? So y goes into y once, y goes into y once, y goes into y once, y goes into y once. So what's in the numerator?
1.
1, right? And what's in the denominator?
Y squared.
Y squared. So I have more y's in the denominator than I did in the numerator. How many more did I have? 2. Right? Now, so while this simplifies to 1, this part simplifies to 1 over y squared. Does everybody see that? Now, there are rules of exponents that you should have learned actually in Algebra 1 and then revisited it a lot in Algebra 2. If you have the quotient of like bases, and this is a quotient because quotient is division. If you have the quotient of like bases, there is a rule that tells you that you can keep the base and do what to the exponents?
You subtract.
You subtract. So that's technically 2 minus 4, which is y to the negative 2, which is 1 over y squared. Do you see how there is a rule? There's an algebraic rule for that. Do we remember our rules of exponents? Yes. Okay. So then tell me, last but not least, what does this simplify to? X cubed over X cubed. What does that reduce to?
It was simplified to just 1, right?
To just 1. So my final answer is just 1 over y squared. Do you see that? Okay. I'm not 100% convinced you know your rules of exponents, so I'm going to give you one more. I'm going to give you one more. Okay, here we go. Let's try that one. So 3 to the negative 2 times x times y squared times x cubed all over 18 to the negative 1, x to the negative 2, y to the negative 4, z to the 0 power. Simplify that. Did we get it? Does anybody want to walk me through how they got it, if they got it? If you're still working, that's fine as well. I don't want to rush anybody. This stuff's important.
Okay, I think I got it.
You think you got it? Okay, walk me through it. What did you do first?
So first, obviously, switch out all the negative exponents.
Okay, all right, let's go ahead and do that. I like it. Why not? Okay, so let me take a look and see what has a negative exponent. So you move this to the denominator as 3 squared. Then you move this, oops, didn't mean to do that. You move this to the numerator as 18, right? Okay, and then this first x didn't move, the y squared didn't move, the x cubed didn't move because those all have positive exponents. In the denominator, we have this negative and this negative. So I'm going to move those up to the numerator, oops, as x squared and y to the 4th. And then this little z to the 0 is still to the denominator. Is that what you got? Did we get that? If you chose to do it this way, and again, there are different ways we can approach this problem. But if you address the negative exponents first, there you go. Does anybody else want to tell me what they did next or what we could do next if you did it this way? What could we do? Someone other than Eric and Reese. Ariana? Natalie? Abiella? What could we do next? Anything.
Combine the x and y.
You want to?
Not the x and y, the x's. And
Oh, okay. So you're saying that we have a product of like bases. So I could combine these, and then I could also combine these. Is that what you're saying? Yes?
Yes.
Okay, so that gives me 18. Now, with respect to the x's, I have x times x cubed times x squared. What is that going to give me? How do I multiply like bases? What do I do to those exponents?
You add them up.
You add them, right? So there's a 1 here, plus 3 is 4, plus 2 is 6. So you should be able to get an x to the 6th. So when you multiply like bases, that's another rule of exponents. When you multiply, because we're multiplying like bases, you add the exponents. Okay, so tell me about those y's. What would be the exponent for y if I were to multiply those like bases?
It'd also be 6.
Excellent. It would also be 6. Now, can I simplify that 3 squared? Can I rewrite that without an exponent of 2? What's 3 squared? Three squared.
9.
Okay. And what about that z to the 0 power? What does that equal?
Zero?
No.
1.
1. Any number other than 0 to the 0 power is 1. Now, I can prove that for you. Look up here. When I had x cubed over x cubed, you said that this simplified to 1. I could also use my rules of exponent that says when I divide like bases, I subtract the exponents. So do you see why if you have a number other than 0 raised to the 0 power, it's 1? And is there anything else I can do to simplify this expression? What would that be?
Divide 18 by 9.
Okay, so I get 2x to the 6th, y to the 6th, and that would be my final answer. Okay, I lied. I'm giving you one more. I'm giving you one more. Okay, let me try this. You're going to hate me, I think, after this one. if you don't already. If you don't see the trick, I'll say that. Yes, I did. I just raised the entire thing to the -2 power. I promise we'll go back to the piecewise functions if y'all get this one right. Okay, here we go. Here we go. There's a couple of different ways we can approach this problem. I'm going to give you a few minutes to see how you would go about approaching this problem. There are many different ways to do this problem. Many different ways to do this problem. Let's see how you do it. Once you think you've got it, if you want to take a break or if you need to use the facilities, by all means, go use the facilities. I'm going to go do that right now because I've been drinking lots of coffee. If you get stuck, feel free to talk to each other. Say, oh my gosh, what did you do first? Oh my gosh, I don't know what to do. I'm stuck.
Hold on. Do you guys know if an exponent has an exponent, you multiply them, right? I don't know if any of y'all know. Trying to confirm. I don't remember.
Yeah, I'm multiply them.
Okay, thank you.
I heard talking, Eric. What did you say? I heard you. What did you ask?
Okay, so I was asking, well, around here, some of the rules of exponents.
Uh-huh.
So I was asking if an exponent has like an exponent, like right now, would you multiply them?
Very good. I love it. And did you get an answer?
Yeah.
Okay, Reese, you said yes, you multiply? Okay. Good, good. I love it. Nathan, did you give it a shot? Did you give the problem a shot?
Yes, ma'am.
You think you got it?
Maybe.
Maybe. Okay. Do you want to tell us what you tried to do first?
I multiplied all the exponents by -2.
Okay, so you distribute the negative exponent first. Yes?
Pardon?
You distributed the negative exponent and everything.
Yes, ma'am.
Okay. So, did anybody else do that first? Eric, did you do that first?
Yes, ma'am.
Ariana, did everybody distribute the exponent first?
Yes.
Okay. Is there another way I could have approached this first? Instead of, that's not wrong, but is there something else we could have done? Yes, I could have simplified inside the parentheses first and then address the negative exponent. But since you had a lot of negative exponents already, not a bad idea to distribute. Nathan, that was clever, because by distributing that negative exponent, you're getting rid of a lot of negative exponents. So that was clever. Okay, so if we are distributing, so I'm going to actually show that step. So I'm giving that negative exponent to every single term. Every base factor. Every base factor gets the -2 exponent. Okay, once you give that -2 to every base factor, as y'all discussed, you multiply the exponents. Power to a power. The rule says keep the base, multiply the exponents. So I'm going to go across the numerator, and I want you to tell me the exponent for every base. So that would be 2 to what power?
6.
Okay, and then x to the
-2.
okay, and y to the
4.
and z to what power?
6.
Excellent. Now looking in the denominator, what is the exponent for 4?
2.
Okay, and x to what power?
-6.
And y to what power?
8.
And x to what power? And that's a negative there.
4.
Okay, now what do we do? What would we do next to simplify this?
But the ones that are negative on the other side of your division line.
Exactly. So that has a negative exponent and that has a negative exponent. So why not move those? Okay, so then that would give me 2 to the 6th, x to the 6th, right? Because this moved up. Y to the 4th, z to the 6th, 4 squared, this moved down, x squared, y to the 8th, x to the 4th. Now what? What could we do next?
Simplify.
Okay, what? Simplify what?
The 2 to the 6th,
Okay. What is 2 to the 6th?
64.
Okay. And we might as well simplify 4 squared, which is
16.
okay. Then what?
And then on the denominator,
You did what?
you can combine the x's.
Okay, so you combine the x's. Okay. Okay, so it, jeez, for heaven's sakes. Okay, it's not letting me choose green. That's fine. So if I combine my like bases in the denominator, what would the power of x be? X to what power? X squared times x to the fourth is what?
X6.
X to the what?
6th power.
Yes. Okay, what else could we do? Anything else we can simplify? I see a lot of stuff going on still. What could we do next?
Simplify the x squared and then the numerator to denominator to get 1.
Okay, so then you looked at this, which was another x to the 6th. So this whole thing reduces to 1. Okay, now what? Anybody else? Any ideas of other things we could simplify? What about these y's? Heaven help me. Why are you not letting me choose green? That upsets me. Okay, purple. What about the y's? Can we simplify those? I got y's in the numerator, got y's in the denominator. Well, what is that going to give me if I want to simplify that?
Subtract them to get y to the fourth in the denominator.
Okay, do you see how that's y to the fourth in the denominator? Ariana, Abiella, Natalie, Nathan, Eric, yes? Do you see how we simplified that to get y to the fourth in the denominator? You technically, if you're using your rule of exponents, you would subtract and you would get this. If you expanded it, that's why it's better to know the rules. 1, 2, 3, 4, 5, 6, 7, 8. Do you see how we get y to the fourth in the denominator? Nathan? Yes? Nobody's answering my question. So sad.
Yeah.
Okay, thank you. And what about that little z? Does it move?
No.
No. Okay, but I can simplify this further. What would it be if I simplified this further?
You divide 64 by 16.
And get what? So there's my final answer, right? Okay. Those rules of exponents are extremely important. You'll need that for pre-cal. You most definitely will need it in calculus. I mean, no ifs, ands, or buts. Okay. Any questions on those simplifying expressions with negative exponents and stuff? We kind of got a little sidetracked, but that's okay. I'd rather go over those and then not go over it and have you continue on in your math career without really knowing that. All right, so let's go back to this beautiful little piecewise function. So we had two pieces. We evaluated x equal -1 using the first equation, which was an exponential equation. And the second one, x equal 4, which equation am I going to use to simplify that? To evaluate x equal 4. Am I using the green or the blue? The first equation or the second equation?
The second.
The second. So if I evaluate g at 4, it would just be 20, giving me that point. Okay. So again, piecewise functions, piecewise continuous functions are functions that are defined by different equations depending on the domain. So, you know, while each of the pieces is continuous, the whole function doesn't necessarily have to be continuous. Okay, this is just a little bit of review. So here you're being asked to write the equation of each line in slope-intercept form, given some information. So here I have a slope, I have a point, here I have a slope, and I have another point. So we did one similar to this yesterday. What is the equation of a line in slope-intercept form? Can you tell me what it is in the what the form is? Y equals what? What are we trying to get?
mx plus b.
Yes, so we're trying to get this. You have been given the slope, and you have been given a point. So go ahead and find me those two equations. Is anybody stuck? Anybody need a hint?
I do. I'm a little confused.
Okay. All right. So if we are trying to write this equation, you have been given the slope. The only thing that you're missing is this b. How are we going to find that b? Well, if this is the equation I'm trying to get, and I have been given a point, can't I use that point and this slope and find b? I sure can. I can come into the equation and substitute in what I know, right? I know the slope is 3. I also know that I have this point here where the y value is 200 and the x value is 50. So can't I solve for b just by substituting in what I know? Right?
Thank you. Yeah.
Of course, of course. So again, a lot of these problems, there's not just one way to do it. You could have used this point slope formula. There's lots of ways to do these problems, but the key is to look at what you've been given, think about what you're trying to get as your answer, and be efficient in you exploiting the information that you've been given. So go ahead and do that for each of those. So we're going to do the same thing for the second one. And in this case, we're going to use that information. And you're going to tell me what B is for each of them. And then we'll be able to write the equations. Were we able to find B? What was B in the first equation? Did we get it?
I got 50.
And that would be correct. So here is our equation, y equals 3x plus 50. Excellent. And you should be able to graph that if necessary. Go to the y-intercept, 0, 50, rise 3, run 1, and connect the points. What did we get for B for the second one?
I got 43.
And that would be correct. So here's our equation for the second one. Excellent. Excellent. Does anybody need us to go over the arithmetic to be able to show that? No? Okay, let's keep going. I would like you to graph the next two. So we have piecewise continuous functions, and you should be able to graph these. Nathan, get ready. And then once you graph them, I want you to state the domain and the range using interval notation. Now, what types of graphs are these going to be? What do those look like? What are all of these? These are what type of functions?
They're both linear.
They're both linear in each of them, yes. So let's go ahead and do that. Let's graph each of these, and then I will walk through them and we'll see if we got them correct. Go ahead, graph. If you get stuck, by all means, verbalize your questions. Let me know. We're getting it? Nathan, how are you coming with those graphs? How are we getting the graphs?
I think I got the first one.
You think you got the first one? You working on the second one, or you stuck?
I'm working on it. I'm on the second line.
Good, good, good. Are we ready to go over them? Eric, yes. Nathan, yes. We ready? Okay. So again, there are different ways to do it. The way I like to graph lines in particular is, as Reese mentioned earlier, I'm going to plot the y-intercept. So I'm going to look at my b value here, and I'm going to say, okay, when x is 0, y is 3. Oh, but it's not defined there, so it's an open circle, right? Because this is only defined for less than 0. So it doesn't include that point. Then from there, I'm going to apply the slope. So I'm going to go up 1 and over 4. Now, graphing at, I would plot this point and then have the graph, but it's not defined there. So what you could do is you could go down 1 and back 4. 1, 2, 3, 4. Do you see how I graph that? That is this part of the graph. Now I'm going to do the same thing with this one. I'm going to start with the y value of the y-intercept so that I can plot the y-intercept. 0, 3. That point does exist because it's true. for x is equal to 0. And then from there, I'm going to apply the slope. So I'm going to go where? Oh, wait, that's not a 3. Heaven help me. There we go. That's 1, 2. I can't count. Let me try this again. Oh my goodness gracious alive. I put it on 2 and not 3. Oh, no. Let me try that again. So for the blue one, 1, 2, 3. Open circle at 3, down 1, 1, 2, 3, 4. There we go. That's more like it. And then this one, 3 is included, and then I'm going to go down 2 and over 1. Down 2 and over 1. Down 2 and over 1. Did y'all get that graph? Yes? Eric, did you get that graph? Yes. Nathan, you got the graph? Yes. Ariana, you got the graph? Everybody got the graph? Okay. What about the second one? What does the second one look like? Well, let me ask you, how many people, and raise your hand in teams, how many people have worked with Desmos? Raise your hand on teams if you've worked with Desmos, the graphing calculator. Eric says yes. Desmos. Ariana, yes. Nathan, yes. Abiella, Ariana, Natalie, have you used Desmos? Reese, yes. I know Reese
I
has.
kind of did.
You kind of know. Okay. I would like you to open up Desmos in another window. And we're going to graph it in Desmos. And you're going to compare it to your graph. Now, I don't know if you've ever done domain restrictions where you've confined the domain to specific values, but I'm going to show you mine. And we are going to, let me see how I can share my screen here. Let me put this in another window. Let me see if I can share now. Why is it not sharing? Is it sharing Desmos? Let's see. Okay, so let's go to Desmos. I don't know what you can see and what you can't see. Heaven help me. Y'all are not seeing that. Okay, let me go to Desmos. I don't know why it's not showing in here. Okay, let me go here. Okay. Move to a new window. And let me see if I can share now. No. Okay, that's poop. Let me go back to my iPad and see if I can get Desmos here. Okay, you can see. Oh, thank goodness gracious. Okay. All right. So if I were to put the equation into Desmos, I would say y, let's do the second one. We're doing the second one. I have y equals negative 3x Okay, and that's going to graph the entire line, but it's only defined for x is less than 2. So to include restrictions, oops, where is my bracket? I normally don't do it on the iPad, so I don't know if it's going to let me. No. There's a brace. Heaven help me. It's not going to let me do it on here. You have to open the brace. Let me see if I can get it to show up in here because it's really not showing up the way I want it to. Let me quit here. Never fails, technology issues. Give me a second. Let me stop presenting here. Let me start presenting here. Y'all can't see that, can you? Can you see my Desmos window or no?
Yes, we can see it.
You can see the Desmos window? Okay, excellent. All right, so let's put this in. We have y equals negative 3x. And if I want to define a domain, I put the open brace and then I say x is less than 2. So do you see how it only goes up to 2? It doesn't include that. So that's that part of the graph. Now, if I want to put in the second piece, it would be y equals x plus 3. But remember, it's only defined for x is greater than or equal to 2. So do you see how, now Desmos isn't going to show you that this point is not included, but this point is included. So the point 2, 5 is included, right? So is this the graph you got for the second one? Did you get that graph? Yes? Can you get that graph on Desmos? You see how I've defined the domain. So this is my piecewise continuous function. I have my 2 rules, and then I defined where the domain was. Yeah? We good? Okay, what I want you to now do is go back to number 1, and you have been given a graph. You have been given a graph, and you are being asked to write a piecewise continuous function. So f of x equal, and then give me the pieces. And I want to see how you're going to come up with the piecewise function. So go back to number 1 and try to do the piecewise function. When you think you have a rule, put it into Desmos and see if you get the right graph. Put it into Desmos. After you think you have the piecewise function defined, put it into Desmos and tell me if you got the graph. And there's a couple of different ways. I know of 2 different ways to get the piecewise function for this. So let's see what you come up with. Oops. And the domain and range for those last two are all real numbers, by the way. So we're trying to write an equation for this piecewise function. When you think you got it, put it into Desmos and see if it works. If you do get it, move on to number 2. How many pieces do y'all see in the first one? Like, how many equations are you going to have? Anybody have any ideas?
2, right?
2? Okay, Eric sees 2. Anybody see a different number of equations? It can be done in 2. If you're clever, it can be done in 2. Anybody else?
You could do 3.
You could do 3. Yes, you could do 3. I could define it in 2 and I could define it in 3. And those are your options. So let's see if you can come up with it. We're trying to come up with a rule, or I should say rules, but a piecewise continuous function. So we'll show each. If you did it in 2, or if you did it in 3. Once you think you got it, put it in Desmos, see if it works, if you get the correct equation, the correct graph from your equations, and then if you get it, move on to number 2. If you think you got it and you graphed it in Desmos and you believe you have the answer, raise your hand in Microsoft Teams. If you're completely stuck and want pointers, little hint to get you started, let me know. Again, graph it in Desmos with the domain restrictions defined and see if you get this graph. When you think you got it, raise your hand in Teams and then you can start working on number 2. If you're completely stuck, Let me know. Oh, Eric, you think you got it. Okay, move on to number 2. Write that piecewise function. So when you got it in Desmos, I'm going to ask you to share your Desmos screen for us to see your equations. So do make sure that you have your Desmos screen with your equations and your graph, and I'm going to make you a presenter, and you are going to share your screen. So I can see that you are able to graph these piecewise continuous functions in Desmos. So Eric, do you have it up and ready?
Sorry, I'm using my phone, so I can't really share my screen.
Oh, okay, that's all right. Don't worry about it. Don't worry about it. So you haven't been able to, but you're able to use Desmos, right?
Yes, I have an app. So,
Okay. Can you, with your camera on your phone, would you be able to aim it towards Desmos and show us your Desmos?
no, not really.
Oh, okay. All right. Reese says she's got it. Reese, would you be able to share your Desmos screen?
I think so.
Okay. Go ahead and graph it in Desmos.
Okay.
And when we're ready, I'm going to make you a presenter, and then you can share your screen if you know how to do that.
Okay.
Natalie, Nathan, how are we coming? Are we getting it? We're not getting it. All right, no. Natalie, no. Where are we stuck? Do we need a hint, Natalie? I can't hear you.
Yeah, can you give me a hint?
I can give you a hint. Of course I can give you a hint. So if you had chosen to, well, it depends how you decide to break it up. Let's say we're doing it in 2 pieces. If I were doing it in 2, well, let me say 3 pieces because I don't know if everybody would see the 2 pieces. Maybe you see this piece, and this piece, right? So I see this, right, defined on this domain. I see this defined on this domain. I see this defined on this domain. Do you see how I can look at this one way and see 3 pieces? Do you see that? Okay, so the first thing I would do is define the intervals where these exist. So I would look at this and say, okay, looking at this interval, it's all values of x less than 0, right? If I start here and I go this way, that would be x is less than 0. Does that make sense? Okay, so then I would have to figure out what the equation of this line is. And you could look at the y-intercept and the slope and write the equation. So the next thing I would do is define this interval. What is this interval? How would you define that interval? All x's between what 2 numbers?
0 and 2?
Absolutely. So I would write that as saying x could be any number, and I have to include this point because it's on the graph. So I would include it here, and then I would include the 2 as well, right? So do you see the domain, the interval for that domain? Okay, now you tell me what the last set would be. What x's does this exist on?
Would it be 2 to, I guess, all numbers greater than 2?
Yeah, so x is greater than 2. Absolutely. Do you see how I write that as an inequality? Okay, so if you saw it in these 3 ways, these 3 pieces, then that would be one way to define the piecewise continuous function. However, there is a clever way to do it in 2. If you saw it, you could say, this is one piece, and then this is the other piece. So it depends on how you see it. If you saw it in 2, it would be x is less than or equal to 2, and x is greater than 2. And I'm not going to say anything more than that. So that should be a hint. There's your hint. Now we're writing the equations. Eric, did you see it using the 2 or the 3?
I solved it using 2.
In 2. Okay, Reese, you saw it in 2 or 3?
3.
3. Okay. All right. So Ariana, Abiela, Natalie, Nathan. Let's finish that one up. I've already given you the domains. So this is the domains for which the function is defined. So you're either doing it using 3 pieces or 2 pieces. When you think you got it, graph it in Desmos. If you got it, move on to number 2. Oh, Natalie's gotten it. Natalie, did you? Oh, no, Nathan. Nathan, did you do it in 2 or 3?
3.
3. Okay, great. And it worked in Desmos?
Yes, ma'am.
Oh, fantastic. Okay, move on to number 2 then, Nathan. Natalie, you think you're getting it now? Yeah? Abiella, Ariana, how about you? Are y'all getting it? You think you got it?
Kinda.
Kind of. Okay, explain kind of. What do you mean, Abiella?
Got the what are they called? The domain.
You got the domain.
Yep, I'm still struggling on finding like the main.
Still struggling on finding the equations. Okay. Ariana, what about you?
Right now I'm trying to figure out how to draw the lines on the
On Desmos?
Desmos. Yeah.
Oh, okay. Okay. Abiella, I'm gonna ask you to tell me what type of line this piece is. Do you see what I'm pointing at? What type of line is that?
I can't see which one I'm pointing at.
You can't see what?
Oh, that one. Okay.
This one.
It's
What type of line is that?
isn't that one still also called linear?
It is a lot. Well, all lines are linear. Only lines are linear. But particularly, what type of line is that? Nathan, can you help her out? What type of line is this?
Horizontal.
A horizontal line. Abiella, do you see that that's a horizontal line?
Yeah.
Okay, so how do we write the equation of a horizontal line? Because that's what's going to go in each of these, right? No matter how you saw it, for x is greater than 2, the equation of that horizontal line is going to go in this spot. So how do we write the equation of a horizontal line? Do we remember?
Y equals 3.
Absolutely correct. So y equals 3 is the equation of this line if it were to go on forever. So y equals 3, y equals 3 is how you would write this as an equation. So that's going to be, I don't know why it's not showing up on here. That's going to be the equation for this interval. Does that make sense?
Yes, that was the first one I got.
Okay. So now, if you saw it in 2 pieces, so meaning you defined it with 3 equations, Nathan, you did it with 3, right?
Yes, ma'am.
Okay, so can you tell me what equation you got for that piece? Because that's what's going to go here.
I got 1x plus 0.
Okay, now in 1x plus 0, so if you're doing y equals 1x plus 0, which is y equal x, what is the slope of that line?
Or it should be y equals negative x. Sorry.
You got it. Y equals negative x. You got it. There you go. So if you wrote it in 3 pieces, the equation of this piece would be y equals negative x. That is correct. Okay, continuing, if Natalie, did you do it in 3 pieces?
Yes, ma'am.
Okay, so can you tell me what did you get for the equation for that piece, which will go there?
I got y equals x.
That is absolutely correct. Nathan, do you see why that one's positive x? Did you get positive x for that one?
Yeah.
Excellent. So if you chose to write it as a piecewise continuous function of 3 equations defined on 3 intervals, this would be it. Okay? But if you were clever and you know different families of functions, perhaps you saw this in 2. And Eric, it sounds like you're the only one who saw it in 2. So I want you to tell me how you represented that.
I use the absolute value of x.
That is absolutely correct. You are absolutely correct. The absolute value of x. So, and we'll talk about this in a day or two. The absolute value function is y equals x. So let me actually write it out. So y equals the absolute value of x can be defined piecewise as x for x greater than or equal to 0 and negative x as, so that's your absolute value function. So you should have seen you should know the absolute value function. We will review the absolute value function, but that's the absolute value function. Y equal the absolute value of x is a piecewise continuous function. It just puts it together. So I could have, Eric, that is beautiful. So who's ready to show me some Desmos? Ariana and Abiella, make sure that you can get them in Desmos. I don't care which one you put in there. So Reese, do you want to share your Desmos?
Sure. Yeah, just
Let me see if I have to get out of my screen. Okay, go ahead, share.
you see that?
I see it is coming.
Okay. Can you see that?
No,
You can't see Desmos?
no, I cannot.
Oh no. Okay.
Use Desmos. So when you go down to your
Okay.
the little arrow, the little rectangle with the, there we go. Oh,
Can you see Desmos now?
it's looking like it's trying to come there. Select something in Desmos. It looks like you're in Desmos, but we can't see it unless someone else can see it and I can't. Eric says no, he can't see it either.
Okay.
It's a white screen.
Well, I got to where it can share.
So down below, you have to share a specific window.
It's only like letting me show the Microsoft Teams window. It's
Okay.
like an option.
Go to the little rectangle. There's a rectangle with an arrow.
I clicked that.
Down below, it should show you different things that you can share.
It says screen and window, and I've tried both of those.
Ah, there it is.
Oh, wait.
There it is.
Okay.
Okay. So you did the second one with 3. So y equals 3 is that little right piece for x greater than 2. Y equals negative. Oh, that is beautiful. That is. Let me take a picture of this. That is beautiful. I love it. Excellent. So everybody should, thank you for sharing, Reese. Thank you for sharing. Everybody should be able to feel comfortable using Desmos and putting in those domain restrictions. You may not have done it with the domain restrictions. So good for y'all. Excellent. All right. So I'm going to let you finish number 2. So let's go ahead and finish number 2, and then we'll discuss that. Excellent. So it's a nice little word problem. You have to write a piecewise function and then graph it and then answer the question. And I think we'll stop after that, and I'll give you a cute little puzzle. And because I think our brains have been working very hard today. And it'll be a good stopping point. This one's tricky. It's a little tricky. When you think you have number 2, raise your hand in Teams, and I will post the puzzle. This one's a little tricky. If you want to graph it in Desmos, that's fine. You don't have to graph it on the graph that's been given. This one's super, super tricky. Okay, Nathan thinks he got it. Grace thinks she's got it. Is anybody super stuck and want a hint? Myself more space. Okay, do we see why there are two equations? Why are there going to be two equations? What do the two equations represent? What's the difference? Nathan, you said you got it. What's the difference? What's the difference in the? I'm sorry?
Could you repeat that?
The question is, why am I choosing to write it in terms of two equations? What are the intervals, the difference in the domains that would require me to have two equations? What's the difference? Did you get it in two equations? Did you write a piecewise function with two equations?
The 1.5 times.
Okay, well, we make a certain amount of money for a certain number of hours, right? And then if we work more than that number of hours, we're going to get a different pay. So where would the change in the graph be with respect to the domain? What are the two, where do the two pieces change?
At 40.
At 40, exactly. So in other words, and we can't work less than 0 hours, right? So I'm going to go ahead and define it only in the first quadrant. But if I work from 0 to 40 hours, I make a certain amount of money. So what would the equation be for working up to 40 hours? What would this be?
Seven times H equals P.
Absolutely correct. Does everybody see how that's the first part? If I'm working up anytime up to 40 hours, I would be working Y equals 7X or P of H equals 7H. $7 for every hour that I work up until 40 hours. Does that make sense? Ariana, Abiela, Eric, Natalie? Does that make sense for the first part? Okay, so then I would have 0, and then if I count by 50, I'm going to count by 50. So 0 to 40 hours, well, that's terrible. I mean, I'm not even going to graph it on here. I don't want to graph it on there. But up to 40, so 10, 20, 30, 40, well, 10, 20, 30, 40, I would be here. And then the graph changes for this part. Now, this is where it gets super tricky. Reese, do you think you have the second equation?
I have a part of it.
Okay. Tell me what you're thinking.
You have to do like 10.5 times H minus 40 if H is greater than 40.
Okay, so if H is greater than 40, you do have 10.5 H, and then it's minus 140. Now, how do we get that?
Wait, I don't know how you got 140.
Okay, well, let's talk through this. To get the second equation, I know that I'm getting $7 for every hour I work up to 40 hours. So actually, let me just say 7 times 40, right? So up to 40 hours, I'm making $70 an hour. Okay. Now, after the 40 hours, I get more, right? How much more do I get? I get a time and a half. Time and a half is 1.5, right? Is it 1.5 time and a half? I get the time, 1, and then a half, 0.5. Now, what is that time and a half of? Well, that's time and a half of 7 times, and then all the hours over 40 hours. So if I work 70 hours, well, I'd have 70 in for H minus the 40 that I'm getting paid $7 an hour. So that difference, all the extra hours, I would be getting paid time and a half. This is complicated. Does that do I need to explain that again? This is for if I just work 40 hours. If I work more than 40 hours, I have to subtract the 40 that I'm getting paid time for, $7 an hour. So this is the excess. Anything excess, more than 40 hours. And all those hours I get paid time and a half for. You see where I got that equation? Yes? Okay, so if I simplify this, I have 7 times 40, which is 280, right? Plus 1.5 times 7 is what? This one's tricky. What's 1.5 times 7?
10.5.
10.5, and that's times H minus 40. So then I have to distribute the 10.5 here. And that's where this comes from. Oops, sorry. I have to distribute. So 40 times 10.5 is 420. I can't write. 420 minus 280 is where the 140 comes from. So that's your second equation. Okay, that one's a little tough. That's a little tough. That requires a little bit of extra work. Are there any questions on that one?
Hey, Miss, I got 7H plus 10.5 parentheses H minus 40. Is that what kind of fun?
Say that again. You got 10
So like,
for this equation here?
yes.
Okay. Say what you got again. 10.5.
So 7H plus 10.5 parentheses H minus 40. I'm not sure if it's correct though.
Okay. Let me write that down because I need to work that out. So you got 7H, which is this,
Mm-hmm.
plus
10.5.
10.5. What?
And parentheses H minus 40.
That is correct.
Okay, so that's fine. Okay, let's just make sure. Thank you.
It's equivalent. It is equivalent. It is equivalent. But this should be 40, right? Do you see why this is 40? It's not H. Actually, let me correct myself. That's not H. This is 7 times 40. because you're only getting paid $7 up to 40 hours. And your H
Oh, okay.
represents, your H represents the total number of hours. So that would be the only change. This would have to be 7 times 40, not 7 times H.
Okay, that's the part I messed up in.
Yeah,
So that's what.
good. Well, that's great though. I mean, that's excellent. You were right there. You were right there. Okay, that was a lot, y'all. That was a lot. So let me, I'm gonna let y'all sleep on that, and I'm gonna show you a little puzzle just to kind of, because that was heavy duty. Let me share just a little puzzle. I'm gonna project a little puzzle, and then I want you to see if you can answer it. Do you see it? So we'll end with that. Just a cute little picture puzzle. Bring it to closure. We're trying to figure out what the last part is. So you should be able to tell me what the banana is worth. You should be able to tell me what the cherries are worth. You should be able to tell me what the apple is worth. And then you should be able to perform the operations. When you think you got it, raise your hand. For those of you who are stuck, oops. 2 bananas equals 30. 4 cherries equal 20. I'm giving you a big hint. Two apples equal 8. So we have a banana plus 1 cherry plus an apple. Oh, times an apple. Okay, how much are the bananas worth?
15.
Okay. How much is a cherry worth?
5.
Yes. And how much is an apple worth?
4.
So tell me, a banana plus a cherry times an apple is worth how much?
35.
35, because we have to do order of operations, right? So we have to do the multiplication first. All right. We didn't get to finite differences and higher ordered polynomial functions. We will start with that tomorrow. Y'all have a wonderful rest of your day. I'll see you tomorrow. Bye.
Thank
Have a good day,
you.
man.
You're welcome. Bye.
Bye. Have a good day.
You too. Bye.